Hello. In this lecture, we will discuss about solving the actuation problem in composites with the help of piezos using MATLAB. So, we will write computer codes and we will see how this analysis can be done. We have seen that this kind of analysis involves a lot of computation. So, this is not something which is to be done manually for even slightly complicated case. So, for that we need to develop a computer code and solve the problem, and that is what we are going to discuss today. So, this is the example structure that we are going to take. It's a composite with a set of layers, and it has two piezoelectric patches at the top and bottom. So, the top piezoelectric patch and the bottom piezoelectric patch are throughout the surface of it. And in this example, there are 6 layers of composites 1, 2, 3, 4, 5, 6, and at the two sides of it there are two piezoelectric patches. So, there are total 8 layers. Among those 8 layers, 6 are composite plies, and at the two opposite surfaces these are piezoelectric patches. This is our axis, x axis, this is y axis. Along the x axis, let us denote the dimension as a, and along the y axis let us denote the dimension as b, and then the piezoelectric patches would be excited with voltage, and we will see the response. So, for that we have had license from MATLAB for doing this exercise, and the license is available in the course portal here. So, there is MATLAB menu, and under that there is a MATLAB access and MATLAB training. So, those who do not have much experience with MATLAB, they can check this training. And however, we are not going to use very advanced features of MATLAB, basic features would do. Now, to access MATLAB, we can go to MATLAB here, and the first two links through the sign up can be done, and after signing up we can access the MATLAB. So, after signing up we can come to this use link, and that will take us to MATLAB. So, if I go to this use link, then it will give us two options. One is open MATLAB online, one is install MATLAB. By going to the installation option, we can install it and use it, and by using this option open MATLAB online, we can do it through the browser. So, here I am doing it through the browser. So, if I open it here, it shows me this. So, the entire MATLAB front end is in our browser now, and these are the codes which has been written. Now, I am going to explain that. So, here we are going to use a symbolic toolbox. So, we will use the symbolic features. Now, initially we should clear all. So, in case there is something in any variable predefined, that gets deleted, otherwise that can create some problem. And then x and y are our symbolic variables which we are defining here. Now, let us define the set of inputs. So, here we have to first input the geometrical features. So, as we have seen that the plate has a length of a and width of b. Length means dimension along x axis, and width means dimension along b axis, y axis. So, a is 0.5 and b is 0.3. Now, there are total 8 layers including the piezos and composites. So, that we are defining here as a variable nn. So, it is nn equal to 8. Now, here we are writing the code in a more generalized way. So, we are considering the fact that the top piezo and the bottom piezo may not be identical in terms of their thickness or in terms of their material properties. So, we define the variables EC top, that means elastic modulus of the top piezo. So, anything with a subscript top means that it denotes the top piezoelectric patch. So, EC top means elastic modulus of the top piezoelectric patch. Nu top means the Poisson's ratio of the top piezoelectric patch. Rho C top means the density of the top piezoelectric patch, and D31 top means the D31 constant of the top piezoelectric patch. Similarly, we have EC bottom, Nu bottom, Rho C bottom, and D31 bottom. They are the same quantities for the bottom piezoelectric patches. Now, here our the quantities that we have given are same, but we can keep it different, and that is fine. Now comes the properties of the composite plies. Now, in here we consider the fact that each ply has same material property and same thickness, but they can differ by, in fact, the thickness need not be same, but we are considering same material property, and their difference is in the orientation of the fibers. So, E1, E2 are the elastic modulus of the each composite ply along two direction. E1 is in one direction, which means the fiber direction, and E2 is in the perpendicular direction. These are all unidirectional plies. Nu12 is the major Poisson's ratio, and then if I apply the formula Nu21 equal to E2 multiplied by Nu12 by E1, that gives me the Poisson's ratio, the minor Poisson's ratio. G12 is the shear modulus, rho is the composite ply density, and theta means the orientation of fiber in each of the plies. So there are 8 plies, so it goes on like this 0, 90, 0, 0, 90, 0. Again, if we go to the figure, this is the first piezoelectric layer. So here the orientation is 0, then 90, then 0, then again 0, 90, 0. So it's an example of cross ply which is symmetric. But again, that's not a requirement. This any kind of lamination sequence that we give, symmetric, anti-symmetric, or whatever, it would work. It even need not be cross ply; it can be angle ply also. Now let us define the z's. So z here means the z coordinate of each of these the two sides of the layers. So at the bottom surface, bottommost surface, we have z1. So here z1 means distance of the bottommost surface from the xy plane with the sign taken care of. So bottom surface means we are going along the negative z direction. So that is a negative quantity, the highest negative quantity in magnitude. And then the next junction, that is z2, then the next one z3, z4, z5, it goes all the way up to z9. Because there are total 8 layers, so there are total 9 z quantities. So if I subtract z2 from z1 from z2, that gives me the thickness of the piezoelectric patch, bottom piezoelectric patch. Similarly, if I subtract znn plus 1, that means the last z to the 1 but last z, so znn plus 1 minus znn, that gives me the thickness of the top piezoelectric patch. And rest of the and then if I subtract znn, I mean if I subtract z2 from znn, that gives me the total thickness of the composite plies. That laminar thickness of the entire composite laminate is that. So these how z's are arranged. So here we go from bottom to top. Now let us give the force input. So here the force can be distributed forces along the x, y or z direction over the surface, or there can be voltage actuation. So qx means if there is any distributed force along the x direction, that is q. So here we are assuming it to be 0. We can give a constant value here, or we can write it as a function of x and y also. Similarly, qy and qz. V top means the voltage that is applied at the top, and V bottom means voltage that is applied at the bottom. Now after analysis, we might be interested in finding out stress strain or any such quantity in any particular point, and that is defined here. xp yp means the coordinate of that particular point, and lp means at which layer. Now here the layer means we are not considering the piezo layer. Here the layer is which composite layer. Again, if we go to the figure, so xp yp denotes the location in the xy plane. So x means the value of the x coordinate and y is the y coordinate, and then comes lp. Lp means layer. So while defining lp, this we call as the first layer, and this we call as the second layer. So the count of the lp layer starts from the first ply layer, not from the, so the count for the piezo lp layer starts from the first ply, not the first piezo layer. So it is 1, 2, 3, 4. So it is 1, 2, 3, 4. It goes up like that. So in our case, LP means 2 means it is this layer. First there is a piezo layer, then layer 1, ply number 1, then ply number 2. After that, we have to go to define the Q matrix. Now Q for the piezo layers are defined considering them to be transversely isotropic. So in the xy plane they are isotropic. So if I know the EC, I just divide EC by 1 minus nu square, and then I multiply the matrix 1 nu 0 nu 1 0 0 0 1 minus nu by 2. That gives me the Q for the piezo layer. So Q1 is for the first piezo layer and Qnn is for the last piezo layer. So here we can see that we have defined Q as a 3-dimensional vector. The reason is that the first two indices are for the Q itself. I mean it's Q is a matrix, so the element goes here. That's why we need the first two index, and the last index is for denoting which layer it is. So this denotes the Q matrix for the first layer. Similarly, this denotes the Q matrix for the last layer. Now we have to find out the Q matrix for the plies. Now while finding out the Q matrix for the plies, because we are starting from E1, E2, nu1 to nu21 and the G, so first we need to find out the Q matrix with respect to the material coordinate, and then we have to transform it to the xy coordinate. Now because the properties of the each ply is same, so their Q matrix with respect to the 1, 2 system is same. That's why we just define it once and we get it. This is the method for that. This is the equation for that we have discussed. And then we go through a loop which goes from 2 to n minus 1, because the layer number 2 means the first ply layer, layer number n minus 1 means the last ply layer. So that's how we traverse. And while doing that, we define the transformation matrix. Here theta is the variable, so theta denotes the orientation of the fiber. Here it is I minus 1 because I starts from 2. So when I is equal to 2, I am in the first ply layer, so that's why I minus 1, it denotes 1. So then we apply the same formula that we discussed, T inverse Q into T, and that gives us QXY, and then we store that QXY in the 3-dimensional vector for Q, and accordingly we get a 3-dimensional vector that contains the Q matrices for each layer. Now that we have got the Q matrices, we have to find out the A, B and D matrix, and we know the relations for ABD matrix, and that's what is done here. And again it has to be added over all the loops. So we initialize A, B and D to 0, and then we write the formula for the A, B and D matrix, and finally at the end of the loop the A, B, D matrix is fully calculated. Now we have to define the basis functions that we are going to use for this analysis. So let's go back to the figure once again. Here the consideration that we are doing in this example, it can be changed also, that's up to the user. Here the consideration is that all the 4 edges are simply supported. And that tells us that at x equal to 0 and A and y is equal to 0 and B, which means that all the 4 edges my W is 0 and the bending moment may be 0, bending moment should be 0. So at x equal to 0 and A, mx is 0, and that tells us that dxx is equal to d2x w by dx2 plus dxy plus d2w by dy2 is 0. And similarly at y equal to 0 and y equal to b, my equal to dxy equal to d2w by dx2 plus dyy multiplied by del 2w by del y2 equal to 0. So our approximation should satisfy at least this boundary condition. If I can satisfy this, that's good, otherwise even satisfaction of this would also serve the purpose. And then we have at x equal to 0 and A, we have v0 equal to 0, and we have nx, which means axx multiplied by del u0 by del x plus axy, which means del v0 by del y equal to 0, and at y equal to 0 and y equal to b, we have u0 equal to 0, and that also the natural boundary condition is ny equal to axy multiplied by del u0 by del x plus ayy del v0 by del y equal to 0. So these are the set of essential and natural boundary conditions. If we can satisfy the natural boundary condition also, that's good. So in this problem, the functions that we have chosen satisfy all the boundary conditions. So these are what we have as phi u's, phi v and phi w. So phi u is sin pi x by a cosine pi y by 2 and sin 2 pi x by a cosine 2 pi y by 2. Now here we have just chosen two terms. We could have chosen multiple terms. In fact, while doing a problem in its entirety, we should keep increasing the number of terms until the convergence is achieved. Here, for the sake of simplicity, just for the demonstration purpose, we are showing it with 2 terms. We could have chosen terms like sin pi x by a multiplied by cosine 2 pi y by b, and also sin 2 pi x by a multiplied by cosine pi y b, and so on. Then there is a variable nu. Nu is the length of this vector phi u. So these basis functions are put in this array phi u, and that is the length of it, and that is nu. Now while discussing the theory, we denoted this variable as m, but here this m might be used for mass matrix also. So that's why to avoid any conflict of variable names, we are using nu here. Similarly, phi u is here, phi v is here, so we are using these functions to define phi v, and nv is the length of it, and phi w, these are the functions used to define phi w, and these are the length of it. So and it can be easily verified that this basis function satisfies all the boundary conditions. Now here we are defining the derivatives. Because we are using the symbolic calculation, so we can easily do the derivatives differentiation symbolically. And in MATLAB, the function that is used to do the differentiation is diff, diff. So diff phi u means which variable I am trying to differentiate, and x means with respect to which variable. So phi u x means derivative of phi u with respect to x. So phi u has two constituents, phi u1 and phi u2. This is my phi u1 and this is phi u2. So it differentiates both and puts in an array phi u x. Then we are finding out the derivative of phi u with respect to y, and then here we are differentiating phi v with respect to x, and then here we are differentiating phi v with respect to y. Now here we are differentiating phi w with respect to x and putting it in a variable in an array phi w x. Here we are differentiating phi w with respect to y. Next we need to calculate the second order derivatives of phi w. So that's what we are doing here. Again, under differentiation, phi w is what we are differentiating, x is with respect to what, and 2 is the order of differentiation. So when we do find out the derivative of first order, we don't need to put the order, but if we are doing it for second order or any higher order, we need to put the order, and that's what we are doing here. So this is derivative of w with respect to x done twice. This is second order derivative of w with respect to y, and it's a mixed derivative of w with respect to x and y. So this is one derivative again, and again this entire thing is put on under another derivative. So that's how the mixed derivative is done. So after having defined these derivatives of the basis functions, now we define the quantities like ni, nw, bi, bw. Because if we go back to the formulation, we saw that our final matrix contains this final equation contains these matrices like mii, miw, kii, kiw, and so on. And to find out this, we need these quantities ni, mii, niw, nw, bi, bw, and so on. And that's what we are doing here. So this is ni. So as per the definition that we discussed while discussing the theory, we have put it. So in the definition of ni, first is phi u, then zeros, then in the next we put zeros and phi v, and this is the definition of nw that we discussed. Now we define bi, which involves derivatives of the basis functions, and that's how it is defined. So again, it's a row, and below it's another row, and below it is another row, and it is bw. It has 3 rows, the derivatives of phi's of different order with respect to different variables. Now we need to find out the thickness of the composite layers, so total thickness of all the composite layers. So we have seen that if we again go back to the image, the total thickness of the composite layer is basically the difference of z at this point minus at this point. So at this point the z is znn minus 1, and here z is z2. So if I subtract z2 from znn minus 1, that gives me the total thickness of all the composite layers, and that's what is done here. And then we have found out the thickness of the bottom piezoelectric patch, which is z2 minus z1, and the top piezoelectric patch, which is znn plus 1 minus znn. Next we find out the quantities that are related to inertia. So we have defined m, s, and I, which are the mass, the first moment of inertia and second moment of inertia, and accordingly they are put in mii, miw, and mwi and mww matrix. Next we find the components of the mass matrix. So again, if we go to the final equation that we use, here we have seen that there are 4 matrices mii, miw, mwi, and mww, and the formulas are like this. So applying Bose formula, we found out the mii, miw, mwi, and mww matrix. Now here one thing to note, here we are doing it symbolically, so we can do symbolic integration and put the limits using the MATLAB symbolic toolbox, but that's not the general practice. In general, these integrations are done using numerical techniques. For example, while using the finite element method, these integrations are done generally using the Gauss quadrature formula. So here symbolically the integrations are done. Now these are double integrals because the domain is 2-dimensional, so we do that integral along x from 0 to a once, and then again we evaluate the integral from y equal to 0 to b. And finally, this has been converted to a double variable. Because it is being done symbolically, it might show it as a fraction. So a double comment converts this entire result as a result to a double variable. So we find out the constituents of the mass matrix. Here, using the same process, we find out the constituents of the stiffness matrix. We already know the formula, we can just apply it and do it. Now comes NP and MP, the block force and block moments. Now these are the relations that we used for block force and block moments. Now this relation for the block force was for one piezoelectric patch. If I want to do it for two piezoelectric patch, we can do it separately and add it up, and that will give us the total block force for all the piezoelectric patches. So here it was considering one patch, and here it was considering two identical patches. So this considers two identical patches. If the patches are not identical, then the formula would be little changed. So it would be Tc. Suppose we are doing it for Tc bottom, so it would be Tc bottom, and here I would have Tb by 2 plus Tc bottom by 2, and same thing here. And accordingly, if I am doing it for the top piezoelectric patch, so it is Tc top. Here it is Tb by 2 plus Tc top by 2. And then we will do it for two patches and add them up. That gives us the total block moment. So here it has been done in that generic way, considering the piezo's can be separate, their voltage can be separate, their properties can be separate. So we find out the NP and MP. So we do it for two patches and add it up, and the added quantity is this, and similarly the added block moment is this. Having found out NP and MP, we can find out the force vector. Force vector has two parts: Fi, the in plane force vector, and Fw, the out of plane force vector. And we are already familiar with the formula for the in plane and out of force vectors. Considering the block force, block moment, and the distributed in plane and out of plane forces, and those also involves evaluating integrals in 2 dimensions, and that's what we have done here. Just we have applied the same integral formula symbolically, and finally after calculating the M, K and F matrix, we are assembling everything here. So that gives us one particular one set of equations. So here, for example, if I combine everything and write it in this way: MII, KIW, MIW. So combining everything, it gives me a big full M matrix, full mass matrix, full stiffness matrix, and full force vector. So then that gives me a equation of the form MQ double dot plus KQ plus F, MQ double dot plus KQ equal to F, by solving which we can find the entire Q vector, which has QU, QV and QW. Now here we are solving it as a static problem, so the mass matrix we don't need. So if here we are just solving KQ equal to F, and there is a command in MATLAB, that's a lean solve. So that solves the system of equations KQ equal to F, and returns the variable here. So Q is our solution. Now once we get our Q, that means we know all the unknown coefficients associated with each of these basis functions. After that, we can find out our quantities of interest, like strain components and the stress components at our point of interest, and we defined our point of interest as a point with coordinate xp, yp and composite layer number Lp. So epsilon 0 p, that means epsilon 0 evaluated at the point P, that is independent of the z coordinate. So we find out the value of epsilon 0 at that point by this. We know that if I multiply the Bi matrix with Q, that would give me the epsilon 0. Now here if I just multiply it, it will give me the symbolic variable, and then if I want to put the value of xp and yp at x and y, we have to use this comment subs under this everything. So this expression, and in the expression x, y should be substituted by xp and yp, and accordingly kappa is defined, and after defining kappa we have to find out the zp, that means the the z coordinate of the point, and we are finding out at the mid location of the Lpth layer. So for that we can just use the formula, and that will give me the z coordinate of the mid location of our layer of interest. Then we can apply this equation epsilon equal to epsilon 0 minus z into kappa, and that is going to give us the epsilon vector, the strain vector. And if I multiply the strain vector with the corresponding Q vector, because it is the Lpth layer, so Lpth composite layer, so absolutely it is 1 plus Lpth layer. So if I multiply the corresponding Q matrix with that epsilon vector, that is giving us the sigma, the stress at that layer. So we have found out the stresses at that particular point. So accordingly, we can be interested in find out stress strains at multiple points. Then we have to define multiple points and we have to put this entire thing under loop. Now we might be interested to look at the deflected shape. For that, what we can do is we can divide the entire surface into a grid point, and we can divide let's divide that into a 20 by 20 grid. So n div x means the division of along number of divisions along the x, n div y means number of divisions along y. So here we define a variable x n and y n, so that will contain the x and y coordinate of our grid points. So if we draw it, it looks like this. So here I have the grid, and by grid points I mean these points. So we are finding out the x and y coordinate of all of these points, and that's what we are doing by that piece of the code. So here we are finding out the coordinate of the grid points, and then at those grid points we find out u, u0, v0 and w. Again we use the substitute comment because we have found out our q. So if I multiply the first nu elements of q with the phi components of phi u, that gives me u0, and here it will give me as a symbol. So on that, if I substitute x and y by these grid points, the coordinates, numerical values, that would give me the actual value of u0 at that point. And same thing we do for v0 and w. So un means the value of u0 at the grid points, v means the value of the v0 at the grid points, and wn means the value of the w at the grid points. It's a two-dimensional vector because I denotes the grid point number along the x direction, j denotes the grid point number along the y direction. So finally, after that we can do a surface plot and we can visualize the displacement. So now after looking at the code, if we run it, so it is running now. If I want to stop it in between, we can just tap the button, it would stop the code. So now it has run and it is showing how w is varying along x and y. Now we have not put the x and y level that we can put easily. So if I type x level and then it is x, the unit is meter, so it puts the x level here. Similarly, y level also can be put. So that's the y level. So it's y direction in meter, and then z level is the displacement w that we are visualizing, that is z level. So it is w. So now accordingly we can plot u0 v0 also. So if I say un and if I just evaluate that particular line itself, that would plot u0 for me. If I say v here, if I evaluate that, that would plot v0 for me. And also we were interested in finding out the stresses which have already been calculated. So if I write sigma p, because that's the variable that we used for the stress at that peer point p. So if I just type sigma p, that is going to give me the sigma p as an array. The first quantity is our stress, normal stress along x direction. Second quantity is normal stress along y direction. This is the shear stress in the xy plane. So this was about the code, considering it as a static problem. If we want to consider it as a dynamic problem, then the entire code almost remains same. Only thing is that at the end here mass matrix would be used, and at the end we have to do the time marching using the Beta-Newmark method. So again, if we just quickly go to the Beta-Newmark method that we discussed. So this was the Beta-Newmark method, considering a system nq double dot plus cq dot plus kq equal to f, and this is the time marching scheme that we discussed. So at first we find out q. So here n plus 1 means n plus 1th time step in our code, that is I. So if we want to follow our code, then in the Beta-Newmark part, n plus 1 is I, and n is I minus 1. So at the ith time step, which is n plus 1 here, so q dot is this entire quantity, which is a function of the q n double dot, q n dot, and q n at the previous time step, which is known to us. Now here we have not considered damping, so these quantities associated with C matrix would be 0. And after finding out qi double dot, we can find out qi and qi dot using these two relations. So that's what has been implemented in the code here. So we divided the entire time domain here the entire time domain t was divided into set of time steps. Yes. So here the delta t is 0.005 that we have chosen. It can be different depending on the problem. And then suppose we are running the analysis till 0.8 second. So we write an array like this that contains values like 0, 0.005, 0.01, 0.015 and so on till 0.8. That means it contains the values of all the time instants, and that is put in an array ti, and nts is the number of time steps, which is in this case that is going to be 161 because our delta t is 0.005 and our ti is 0.8. And also the forcing the voltages can be a function of time. Similarly, the qx, qy, qz also can be function of time, and here we have assumed that they are function of time of the form omega t. So it can be the voltage can be v sin omega t, qx can be q sin omega t, and so on. So for that we have defined the corresponding omegas. So omega x means the frequency corresponding to qx, omega y means frequency corresponding to qy, and omega z means frequency corresponding to omega means, so here omega x means frequency corresponding to px, omega y means frequency corresponding to py, and omega z means frequency corresponding to pz, and omega dd, omega q dd is the frequency corresponding to the voltage. So this voltage also can be a function of time. So if it is sin omega t, the corresponding omega is this. So what we do here is we run a loop. So initially we initialize the quantities q, qd and qdd to 0 because at the initial time step time t equal to 0 everything is 0, and in beta numeric method we have some parameters beta and gamma. We have set the parameters here, and then we are running a loop from 2 to nts, number of time steps. Now in the here the force matrix has to be calculated at each and every time step because that's a function of time. So we have multiplied the expression of the force matrix into a quantity sin omega t, and the omegas, whether it is omega x, omega y and omega z, that depends on which component we are evaluating. So here we are evaluating it corresponding to the voltage, so it is omega q dd, and here it is corresponding to the force along x and y, so it is omega x and omega y. Now we after evaluating this fi, we have got fi and fw as a function of time. We get our force vector at each and every time step, and then from that, using the technique that we described, we find out q double dot. Q dd means q second derivative of q with respect to time. Qd means second derivative of q with first derivative of q with respect to time, and q is q. So we evaluate that at each and every time step, and we do the time merging. And after evaluating at each time step, we might be interested to find out u, v, and w, or quantities like epsilon and sigma that we discussed before at our points of interest at each and every time step. So here we are evaluating up, I mean u0, v0, and w. So here we are not evaluating u0, v0, w in the entire grid. Rather, here we are evaluating at only one point. We could have found out u0, v0, w in the entire grid also as a function of time, but we are not doing that here to keep it simple. So we are evaluating u0, v0, and w at point p at every time step, and that's what is done here, the same substitute command, and here we are finding out sigma, and the time loop ends. So if I run this code now, so here we are printing this I. So if I look at the command prompt, I can know at which time step the code is running. So it is soon going to be at 161st time step and come out of it. Now if I want to find out w as a function of time, so we have seen that w is a one-dimensional array now because we are not evaluating w at each and every point. We are evaluating at only one point, so the only index that it needs is the time index I. So if I evaluate w as a function of time, so ti is the time and corresponding w. Okay, so it was wp, not w, the variable. So you can see w has been evaluated here. So w is varying as a function of time in this fashion. Accordingly, we can plot the variation of sigma, variation of epsilon, and variation of other displacement quantities, and we can put the xy level also by using the command that we saw, or by using these buttons x level, y level, and so on.
Hmm.
So that was an overview of how we can do it using the how we can do these calculations by writing a simple code in MATLAB. And again, the code is written has been written in a more generic way, so the piezoelectric patches can be different, and the basis functions that we have chosen here are sign functions. Depending on the boundary conditions, they can be different, and accordingly proper basis function has to be put. So with that, I would like to conclude this demonstration here. Thank you. Then comes LP. LP means layer. So while defining LP, while defining LP, this we call as the first layer, and this we call as the second. You might have to order something. I think I can just fix that.
When you compress a gas like air, it gets hot. If I take a compressed gas and then let it expand, it gets colder. So when gases expand, they cool down, end of story. But maybe not. We got room temperature 73.9. Open the valve, and it quickly increases to 75.4. It's actually warming as it's coming out, not cooling. When you open the valve, the change in temperature divided by the change in pressure is always constant. This constant was called the Joule-Thomson coefficient. If the Joule-Thomson coefficient is positive, then the gas expands and the temperature drops. But there are some gases that have a negative Joule-Thomson coefficient at room temperature. The Joule-Thomson coefficient is temperature dependent. Past 600 Kelvin, even nitrogen will heat up when it expands through a valve. In fact, once any gas gets hot enough, it will heat even more when you expand it through a valve, not cool down. When you compress a gas like air, it gets hot. If I take a compressed gas, For me, exercise means as when you finish exercise, you feel, you sweat and you feel very fresh, but your body shouldn't really get tormented by the exercise. That is not going to help anybody. And there is no proof to show that people who do this extreme exercise, they live longer or they have a better quality of life. Certainly not. We have seen all these people who are practicing heavy weight lifting, and when they grow older, they have their own problems with all this wear and tear. If they're there, they have to exercise for, there's a place for people to exercise for half an hour, 1 hour, when feel very good. That's the best thing what can happen, but not to get into this kind of a very irregular exercise habit, doing too much of exercise in a short period of time, yeah, which cannot be very good for the human body. Anyone. नमस्कार यानी वेलकम टू स्टडी क्यू। मैं हूं प्रशांत अमन और इस वीडियो में हम बात करने वाले हैं एक बहुत ही इंटरेस्टिंग टॉपिक के बारे में। हाल ही में चाइना देखिए अपने सरकारी आर्टिकल इंटरनेट से डिलीट करना पड़ा। पहले बात चाइना ने जयशंकर साहब के साथ कुछ ऐसा शेयर नहीं किया है। चाइना ने जयशंकर साहब को टारगेट करने से बहुत ज्यादा